My name is Tom Pinckney. I'm from eBay, and I'm going to be talking about a recommendation system that we're building. So for about the first 2/3 of the talk, I'll be talking more about the theory behind the recommendation system, sort of how conceptually all the pieces work. And for the final third, I'll be talking about sort of how we use Cassandra to actually implement this and handle the scale that eBay needs for this kind of recommendation system to work. So when we think about a recommendation system, there are a bunch of different parts. There's understanding what the user's intent is, that, hey, they're looking for shoes. There's understanding their kind of unique context, like they're a size 12, and so any shoe that we show them that isn't a size 12 is kind of an irrelevant recommendation. And then there are matters of taste and aesthetics. So what color, what style, what are all the intangibles in those shoes that are going to make the person really want them and like them? So all three of those are sort of big, difficult questions. And for this talk, I'm just going to really talk about the taste and aesthetic part. How do we model and try to understand and predict what someone is going to like? So we think of this as the model of what someone's going to like as a taste profile. So our first challenge is, how do we build a taste profile? How do we understand what you're going to like, what you're not going to like? Well, the kind of ideal goal is that we would have a list of everything that you like and a list of, for me, like everything I don't like. So my taste profile might be that I like hiking to this cabin in New Hampshire, and I like Python, and I like reading the New York Times. I don't like plaid shirts. I don't like sushi. That was a terrible romance novel. I don't think it was one of her best. So now the problem is, this is kind of like having a full-scale map of the world. It's perfectly accurate and not very practical. There's no way that you're really going to get this list from someone of everything they like, everything they don't like. Even if you could get them to sit down and tell you these things, study after study has shown that people aren't very consistent in their own opinions about what they like or don't like. So just for example, there was a study where people were shown a list of things and asked whether they like them or don't like them. And then 2 weeks later, they were shown the same list and asked again whether they like them or don't like them. And their answers were only about the same 80% of the time. So there's a sort of an upper bound as to how much you can ask people, even if you could have infinite patience from them. So our challenge is, how do we build a taste profile for someone? And our sort of core thesis is that all of the things in your taste profile are not unrelated, that your likes and your dislikes are all highly correlated. So one of the things that we did previously at the startup, we were at a startup called Hunch that was bought by eBay about a year ago. We surveyed lots of people. So we surveyed tens and tens of thousands of people, and we would ask them all sorts of questions. And one of the questions we would ask is, do you like President Obama? Do you support him? And another question we might ask would be, do you prefer arugula or iceberg lettuce? And what do you know, but the old stereotype of arugula-loving liberals is true. So if you sort of look like the guy at the bottom, like where I grew up in South Carolina, you probably prefer iceberg lettuce statistically. And if you voted for Obama, you have a bias toward actually liking arugula. So this idea that things are correlated starts giving us a toehold or a way in to try to build a taste profile for someone. So let's start thinking about this, trying to figure out how to formalize this a little bit. So in this drawing, what we have is red circles represent users. So we have a user, A, and another person, B. And then we have some things. So we have like the Republican Party, and we have arugula, and we have all sorts of different things there. And when green arrows represent a user liking something, an express preference. We've asked them, they've told us they've liked this thing. A red arrow represents a dislike. They've said they actually dislike something. So we have here user A has said they sort of like the Democratic Party, they like arugula. We have some other user, they said they like the GOP party and they dislike arugula. So if we have some new user that we don't know a lot about, this user C, all we know is they've liked the Democratic Party. Well, sort of we squint and look at this and go, probably from what I know here in this drawing, they probably would like arugula, because the only other person in this drawing who has liked the Democratic Party also liked arugula. So it's getting to the idea that we're trying to find either somehow similar people or find similar patterns and connections to other people. So let's try to sort of zoom in a little bit more detail about how we try to think about that. So imagine we plotted in sort of 2 dimensions, one in the x-axis Maybe you can rate in stars from 0 to 5 how much you like Obama, and the vertical axis, we've asked you maybe 0 to 5 stars how much you like arugula. So now we can start plotting people in this two-dimensional Obama versus arugula space. And if we actually survey people, we see maybe not as exactly this data, but something similar to this, where maybe that user A from the prior drawing is in the upper right corner where they like Obama a lot and they like arugula a lot. User B from the prior drawing who like the GOP party is in the lower left quadrant. And we have some other people in there. And now we have this new user, user C again, who are trying to figure out their arugula preference, given that they've said they are on the x-axis at a known point. They like Obama a certain amount. So the question is, where on the y-axis do we think they fall? And we can answer that question by doing something like a linear regression through the data points. We see that there's really this better axis for understanding this data set. It's really more powerful to understand this as a matter of sort of this concept of maybe political orientation versus trying to think about it in terms of lettuce and specific candidates. That we see that this user C falls on this regression line at a certain point. We can now infer a y value for them, how much they like arugula. We can also do some other interesting things. We're not just plotting people on this line. We can plot things like the lettuce, like different candidates. And so we can start intuitively thinking that similarity is somehow based on geometric distance along this line, so that user A is close to arugula, which captures this idea that they like each other or they're similar. User B is very far apart from user A on this line, sort of capturing the idea that users A and B are very dissimilar from each other. And instead of just doing this in one dimension around political affiliation, we can do this around many, many dimensions. So we can find what are called many latent factors that help explain people's behavior. So these are factors that typically are predictive, but are very hard to directly measure. So it's very difficult to ask someone, where are you on the introverted to extrovertedness scale? But it's very predictive, generally, in terms of predicting what they will like or dislike to understand where they fit on that scale. So what we're doing here is we're finding things that people have clear preferences on, a specific product, a specific concept, taking their known preferences from those very specific cases and using that to map them onto these more predictive scales. One of the interesting things here is that we didn't pick these dimensions ourselves. The machine picked them. So the algorithms picked the dimensions that were most predictive for the either millions of Hunch users or the hundreds of millions of eBay users. And interestingly, the dimensions that get picked turn out to match roughly very similar dimensions that sociologists use to describe people. So if you look at like the big four personality model, most of those first four factors about people, one of which is introverted versus extrovertedness, is something that also very much shows up in our data. So in some ways, it's kind of an empirical validation that these are, at least the first few of these dimensions, are some of the basic ways that to think about people and understand people's differences. Now, in our particular models for doing product recommendations, we use about 50 of these different factors. So once you get past the first maybe fifth, 5 or 6 of them, it becomes very hard to figure out what they are. The algorithms aren't labeling the axis that this is the masculine to feminine axis. What it is saying is there's an axis that stretches from lipstick and mascara to, again, these are all sort of, in some ways, kind of the stereotypes of the data in some ways confirms, from lipstick and mascara all the way to sort of cordless drills and a lot of other sort of stereotypically masculine products, right? So we sort of look at that and say, oh, this seems to be roughly masculine to feminine. Once you look at the sort of degree, once you look at these axes that the algorithms produce above like the first fifth or sixth of them, it becomes pretty hard to add a sort of human intuitive explanation of what they are. But the key idea is that we can plot people and things into this high-dimensional taste space where proximity to each other equates to similarity and distance from each other equates to being dissimilar from each other. So now, going back to this original idea of how do we build a taste profile, we have a little bit of a simpler problem. Instead of enumerating every single thing that you like and dislike, what we now need to do is build a plot everyone and everything into this high-dimensional taste space, because then all it's a matter of doing is doing distance calculations to each other to figure out what you like and what you don't like. Things that are far away from you are things that are going to go into the don't like bucket. So then the question is, how do we actually calculate these taste coordinates? Now, this is a little bit sort of a quick, so I apologize if I'm skipping over some details here, but going back to that original example earlier of the user A, B, and C, and the lettuces, what we can do is start adding some numbers here to make it a little bit more, to build a little bit more of a formal model here. So for every user and for every thing, I'm showing coordinates. So that's where they are in taste space. So user A is at coordinate location 1, -2. User B is at -1, 2. The arugula is at coordinate 1, -0.5. How do we come up with those coordinates? Well, I won't go into the details, but we have this requirement that we think of every green edge in this graph, every like, as having just somewhat arbitrarily the value 2. And every red edge, representing a dislike, is having the value -2. And then we say that the user and the item connected by that edge have to have a dot product of their coordinates that equals that edge value. So this means that in the case of the A and the lettuce, dot product means take the x value of each, multiply them together, add them to the product of the two y values. So in this case, the two x's are 1, the two y's are -2 and -0.5. You do the math, and that does indeed equal that edge value of 2. You can sort of think of it as the edges are adding constraints on where the coordinates can be in space. And the dot product is just one way of expressing that constraint. So using this, we can figure out what the coordinates are for the democratic node in this drawing, that whatever his coordinates are, they have to satisfy the constraint of the dot product with user A has to be 2, and the dot product with user C has to also be 2. You see the two simultaneous equations that result from this. There's a solution to those equations of x equals 2, y equals 0. So that is the coordinate in this system for the democratic donkey here. And the sort of the key point there is that these coordinates are being picked in a way where their position relative to each other ends up giving you meaningful insight about similarity and dissimilarity. So now, that's sort of how you might, just given a static configuration of a known set of preferences, come up with the coordinates for everything. But on a site like eBay, you don't just have a bunch of data about people ahead of time where you just take all this transaction history, you look at purchases, call every purchase alike, and compute everything. That you've got people that, they're buying stuff constantly, new users are showing up constantly. So new things for sale are coming up constantly. So we can't just statically compute everything. We have to do this incrementally in real time and have this work. So imagine you start in a situation where you're on the left side, where you have some user C who likes this SLR camera, user A likes this camera lens, user B doesn't like that camera lens, but they do like this point and shoot camera. How do we change everyone's coordinates in taste space when we get some new piece of information in that, for example, user A has just bought this SLR camera. So there's a new green like edge going between A and the camera. Well, we now resolve these simultaneous equations. We know that the camera has to satisfy the requirement that it dotted with A equals 2, and it dotted with C is also 2, and that, I don't know if you can see in the slides here, but the coordinates for the camera and A have changed from the left-hand to the right-hand side based on this new piece of information. So this is the process of folding in a new incremental piece of information to change the coordinates of where things are in taste space to, in this case, make A and the camera and the lens sort of all move closer to each other a little bit, because in some sense they are all similar. They're all liked by the same kind of person. So now I'm going to talk a little bit more about how we actually implement this. So sort of less about the theory, more about how we actually sort of are building this. There's two halves to the system. One half is this updating asynchronous process that happens decoupled from individual page loads on the site. So if someone comes in and purchases something, an event is triggered, goes over an event bus, is eventually received by our updating processes, and they then add this new edge into this graph structure. So this entire graph structure is what we call our taste graph. That's what's stored in Cassandra. So we get this new event, we store it into the Cassandra graph, and then we update all of the things that are sort of affected by it. So in the prior example, if we just got this new purchase between A and the camera, we add that edge between the two, and now we go update A and the camera's coordinates. And we do that by having to go look up all of the other edges connected to A and that coordinate. So we're reading all the sort of adjacent nodes and edges out of the graph, recomputing all of their coordinates, and then storing that back into the graph. We also store all of those updated coordinates into a separate database that is used purely for serving recommendations at runtime to customers. So that's the second half of the problem, is when a page load comes in, so say someone is looking at this compact camera, that makes a call over to our recommendation engine to say, hey, I need, say, 5 recommended alternative cameras that this user might want to look at. We go query in this recommendation database. We know the user's coordinates, so we know the coordinates of the person who's looking at the page. We then go find all of the other cameras that have coordinates very close to this user. And so because that represents similarity and predicted affinity between the user and those cameras. And then we show those, maybe we take the top 5 cameras that are closest to the user, and those become that user's recommendations. So this side of the problem is optimized basically for just very fast read-only performance because ballpark, we will probably, when this is not fully ramped out right now, this is serving maybe 10% of traffic on one page right now. And it's already doing about, at the busiest time, about 15,000 recommendations a second. So as we ramp, and that's just in North America. So once we ramp up globally to 100% traffic across all pages, we're going to be doing many, many hundreds of thousands of recommendations a second at our busiest peak. So that's why this whole path is just optimized for read-only scalability, as making things as fast as possible. So zooming into that Cassandra piece, where we store our taste graph of every user and everything and all the connections between them, we have, in this first version that we've built, about 40 billion different edges in our graph, connecting about 2 billion eBay listings, things that are for sale or have been for sale, connected to about 200 million different users. That's about 5 terabytes of data. We replicate everything twice, so about 10 terabytes of data. And this is a very small starting piece, since we're only looking at a few key signals right now. So things like purchases and bidding on an auction and things like that. There are a whole bunch of other signals that we want to bring into the graph to express new types of connections between peoples and things that will probably result in a roughly quadrupling of this. So we estimate eventually we'll probably be at around nearly 200 billion edges in our graph stored on Cassandra. We're in the process of upgrading from a 16 machine to a 32 machine cluster. These are beefier machines, so we're looking forward to that beefier node support in the future. The machines are connected to an SSD disk array over iSCSI and 10 gigabit Ethernet. This is not necessarily the ideal sort of set of hardware SKUs for this, but it's, for a variety of reasons, a kind of preferred SKU within eBay, so it's what we use here. It's got a huge amount of I/O capacity. The disk arrays do about 400 to 500,000 I/Os a second. So it's a little, and there's a lot of RAM obviously per machine, so it's a little bit different than maybe the ideal SKU. We're using, as you see, Cassandra 108. We're on size tiered compaction for now, though moving hopefully shortly to leveled compaction to improve some of the read latency. We want to get more people, more apps, some other apps besides this recommendation app running on this data store. And some of them have even stricter read latency requirements. So we think that level compaction will be great for us. And we're also really looking forward to Bloom filters and things like that being off heap. So we're running with an 8 gigabyte heap right now, because otherwise we start seeing some pauses that, again, affect latency. So we're really looking forward to getting stuff off the heap. The schema for how we're storing this data is that the edges are basically wide rows where we just, for a given user, if we represent 10 edges between them and 10 things that they have bought or bid on the site, we just keep adding new columns to represent each edge. And there are different types of edges, like a purchase versus a bid. We treat them differently in terms of how we weight them in some of our calculations. So we're recording the edge type, the item ID that the user is connected to by this edge. We also store all this data a second time from the item's point of view. So this just makes it fast to index and look up and retrieve the data. So since sometimes we want to say, what items is this user connected to? And other times we want to say, what users is this item connected to? So we index all the edges from the item's point of view as well, in the same way that every column is a list of the users connected to that item. And then finally, we store the coordinates of every user and every item. And in our case, we're using a 50-dimensional space. So every user and every item has 50 floating point numbers to represent their exact coordinates in that space. On this first version, this is showing read performance of the number of rows or keys being read per second. Since we have very wide rows for edges, a single edge can be read by a single key, whereas our nodes are not wide. There's one taste vector or one coordinate per node. So our read performance, if you look at number of keys read per second, is dominated by nodes. Because a single read gives us all the edges for a user or an item. But we're today at our busiest time doing about 50,000 reads a second off of the cluster. And this was actually benchmarked against the 16 machine cluster. So we think that as we double or quadruple the amount of data, we're going to continue to be able to get very good read scalability from our 32 machine cluster. And then writes per second is around somewhere between 3,000 and 4,000 writes per second. And we're doing a write every time someone does some action on the site that causes us to update their coordinates, their position in taste space. So today, purchases, watches, bids, things like that. So that's how we're thinking about building and working on our next generation recommendation system, how we're approaching the taste and aesthetic modeling part of the system at eBay. I'm happy to talk about some questions, and also happy to have Vulcan Gorel, who's the engineer here, who actually built all of the Cassandra side, who can get into tons more details than I probably can. But,
I actually have a question on the recommendation engine side. My understanding is that most large-scale recommendation systems use some form of item-to-item matching, so YouTube and Amazon, for instance. So it sounds like you're doing more user-based, so I was curious what your reasoning was there.
Yeah, that's a great question. So we think it's more powerful to understand the user versus understand the item-to-item affinities. So it may be that you and I are looking at a book, but when you think about the other books that you might want to recommend to us, that's partly informed by the book we're looking at, but it's also partly informed by who we are. And so if you just do item-to-item similarity, you lose that second dimension of the problem. So there might be many different types of people that are all interested in a particular book, but for slightly different reasons. And we want to be able to capture that so that the other books that we recommend take advantage of that additional information we have. There's another difference between sort of the eBay recommendation problem and nearly sort of every other retail recommendation problem out there, which is that eBay's listings are sort of all unique. So people put up a picture, write a title, write a description. If it sells within 7 days, great. If not, people typically take it down. So that sort of entity pops in for existence for 7 days and then disappears. And so you have a lot of difficulty if you want to build up an item-to-item model. You're not going to get much of a signal. You're going to see that, oh, well, 50 people looked at this item, and 10 of them bid on it, and those 10 people didn't then do really much at all in common with each other again. So you're not going to see, like on Amazon, you might say that, well, 10,000 people bought this book, and then disproportionately a large number of those 10,000 went off to buy this other book, because both books have been for sale on Amazon for 2 years. So that's how you can accumulate 10,000 data points about each one. So you can do that item-to-item similarity directly. That's never going to happen on eBay. No.
What are you doing with the extra RAM?
We have some side projects. No, so buffer cache still gets that extra RAM still gets used for buffer cache. That the working set, the data file set is bigger than physical RAM, and so that buffer cache is very valuable. There also is there is some ability to store some data off heap already in the existing versions of Cassandra too. So we use some of that. But the simple answer is buffer cache.
You talked about recommender system, right? So I have a very, very simple question is,
Those are always the dangerous ones.
Yeah, exactly. The danger is you can recommend all you want. I'll tell you, analogy is you can only take a horse to the water, you can't make it drink. And what do you do when people don't buy your stuff? And do you reuse it? Does it automatically get a new algorithm, or are you developing a new one?
Well, it's a good point that there are several parts. That you can't just make a recommendation. You need to be able to justify it and explain it to people. So you might have the best idea in the world for what someone should buy, but if you can't explain it to them, then they're not going to necessarily understand your brilliance. So partly one of the things we think about is how do you try to justify this? And so there are very simple things that people do, like just the old people who bought this bought that. You're trying to provide an explanation that, hey, many other people have done this. Maybe you should look into it too. There are other things that you can try to do, like in the case of books, you can say, hey, more by this author, right? So these are very basic things, but they do help explain why you're making the recommendation. The other part of it, though, is if we do make a recommendation, we track and log, that we showed you these 5 things, and you didn't click into any of them, or you clicked in, which is a little bit harder to interpret. Like if you didn't click into any of them, does that mean you just didn't look at them and so didn't notice our recommendations because they were maybe lower on the page? Or does it mean they were all really bad? It's hard to figure out. If you click on one of them, but not the other 4, then that actually tells us something pretty informative. That means that at least of those 4 or 5 recommendations we showed you, the one you clicked on was somehow the best one. If you went on to buy it, even better. And that somehow the other ones were less good recommendations. And so we can infer some negative feedback against those from you. So over time, our model will start getting a little bit smarter about you not liking those kinds of items. So even though you didn't actually sort of X them out or say this is no good for me, by behavior, you showed that you preferred other ones better. It's one of these, so on the hunch side, before we were part of eBay, we used like who you followed on Twitter and what you had liked on Facebook. Very, very informative. So less informative exactly about who your friends were on Facebook, more informative about what you had liked and what your interests were. Very informative on Twitter about who you followed. In the shopping context, right, you've got a bunch of different challenges. So a lot of times people come to the site and they're not logged in. The first thing you do when shopping usually isn't log in. So unfortunately, the way a lot of retail works is you log in only at the end of the process. So even knowing who you are at the start and knowing much less who your friends are and things like that is not immediately available all the time. The second thing is just that, a lot of people say, look, why are you asking me who my friends are? I just want to buy this, pair of shoes. So there's sort of like 5% of people that are sort of excited about that. And they want to say, hey, what do you think about this shoes? I'm thinking of buying it. Look at the great deal I got. And they do want to engage with their friends about it. The other 95 just wants a good price. And they want to find it and get on with their life. You're telling me. Yeah. So the question was that finding latent factors in a large sparse matrix is very hard. And so the matrix here is every user versus everything. And for every cell, we have a did you buy it or bid on it. And the vast, vast majority of these cells are empty because most people have not bought or bid on most things. So maybe 1 in 100,000, 1 in a million, 1 in 10,000 of these cells are filled in, and the others are all unknown question marks. And our sort of job is to fill in the rest of those cells with a prediction about whether you would like this or not. So it's very difficult to computationally very difficult, to find latent factors in a very large sparse matrix like this. So the high-level approach is a method called alternating least squares, where in some ways you can think of it as start with a set of random factorizations or a bunch of random coordinates for people, and then incrementally improve them. So initially, if we pick random coordinates for you and that camera, and we know you like that camera, the dot product's probably not going to be close to our target of 2. So let's tweak your coordinates and tweak its coordinates until it gets closer to 2. It's still very computationally intensive. I mean, the matrix factorizations, when we just do a straightforward matrix factorization, take weeks to run on a 50-core machine with hundreds of gigs of RAM. And that's with us hand-tuning the assembly to make sure the inner loops of the matrix multiplies are as cache efficient and as fast as possible.
When a new event comes in, I guess you limit the propagation.
Yeah, we have heuristics about, I mean, in some sense, you want to update your neighborhood in the graph until the changes aren't very significant.
Is there any reason that you guys chose to, I mean, it sounds like you guys rolled your own in some sense, but instead of using, say, like Titan or Agamemnon or something that already sits on top of Cassandra? Or is that sort of a legacy hunch thing that you guys brought into eBay?
A little bit of both. So we did try a bunch of different systems, and generally, because of the scale, one of the things is that even if it doesn't necessarily at first seem to make sense to spend effort to optimize something, every 5% turns out to actually matter a lot here because the size is so big. So building something ourselves, as long as it wasn't too complicated and too hard, made sense. And in this case, it turned out it's actually not that hard to represent a graph in Cassandra. It's pretty straightforward. It just kind of works. It made sense just for us to do that. We also already had all the algorithms we were running on top of that graph. So one of the reasons sometimes to use an off-the-shelf graph database or graph package is not necessarily so much for the data storage representation, but for the algorithms that run on top of it. And we already had the algorithms that were running on top of it also. So that just sort of took away another reason to do that. But I'm not swearing that we made the right decision. It was. We definitely strongly prefer using open source options whenever the possibility is because it's obviously less for us to do and less to go wrong. But this was simple enough that it seemed and could be optimized enough that it made sense for us.
Yeah, over here on the left.
Sure.
How long has this been, I guess, live, or how live is it? And had you looked at other solutions, and what decision making process did you use? And what else did you look at? That kind of.
Sure. So this is this sort of next generation platform is basically in very limited testing in North America right now. So at peak, maybe 10% of people going to eBay on certain pages will see recommendations powered by this system. So it's basically the very, very early stages of being rolled out. I know that, so I've now been at eBay for about a year. So I was at this company Hunch before. I know eBay has spent a number of years looking at both outside vendors for this problem, as well as building a internal solution. And I think the reason that frankly, all of the external vendor solutions had failed previously was sort of getting around these problems of how real-time this has to be, that people and things for sale appear constantly, they disappear constantly, and then separately, the idea that there's no catalog, there's no product catalog that says these are all the same item. It's just 100 different people might be selling Adidas sneakers. Maybe they're the same, maybe they're not, maybe they're subtly different due to condition because they're used and things like that. So a lot of the outside sort of historic solutions that people had tried and looked at really depended on this sort of item-to-item collaborative filtering, where you had a strong sales history for this SKU, and you could see that what other SKUs people went on to buy. And that pattern took months, years, quarters to develop and be discoverable. And that's just not a situation that exists at eBay. Nothing sticks around for months. It's much more dynamic. Yep, and those are all really hard problems that we don't have, I won't say that we've solved. The one piece, you asked a couple different things. So about, for example, maybe I click into one item, but it's not really right for me. There's some simple things we can do, like how quickly do you bounce back with a back button, right? You know, if you click into something but immediately bounce off, that's actually probably more of a dislike than a like. If you then go on to buy something else that we showed to you, we have an attribution problem. So one of the things we're trying to understand is, can we track everything that you were exposed to through these recommendations, and whether you clicked on it or not, but just that it was an impression, and then look weeks, months later whether you bought it. That gets hard, especially in a multi-device world, because I saw it on my computer, but then I searched for it on my iPhone when I was waiting for the train. And I did both while not logged in. So you don't know that it was Tom in both cases. In the cases where it gets easier is where I do it on the same device, or I'm logged in both cases, and you can look, sort of stitch sessions together over time and say that, well, actually 2 weeks ago Tom was exposed to this, and then he went through sort of this research phase, and then he finally went to the purchase phase, and he actually bought one of the things that he was first exposed through the recommendations versus being first exposed through search. So we're using, honestly, only a tiny fraction of the data we could be using, and that's why I call this kind of the V1 version, where we're looking at a couple very basic factors or behaviors of people, like what they've purchased, what they've bid on, what they've watched. We have a list of literally nearly 100 additional factors that we would like to use. It's just that we're taking a fairly deliberate process of every time we consider a new factor, we add to the model. We see if the model's predictive power goes up or down through analyzing things like prior purchase histories, doing things like crowdsourcing human judgments, where you get a few thousand people to look at the new algorithm versus the old algorithm. So it's a fairly laborious process to add additional factors to the model. Sure. So this where it sort of veers a little bit also into all those other parts of making a good recommendation that are not about taste. So going back to say, let's think about a book recommendation. Part of the issue is, well, does the user even want books right now? Generally on eBay, we sort of solve that by being fairly simplistic. If you're searching for books, looking at books, we take that as your intent, and we show you more things like that. So we can solve the intent part. Then comes the context. Well, when books, like I don't want to recommend a book you've already read, ideally. So it gets into doing things like at a minimum, we should look at purchase history, try to figure out what books you've already bought, not recommend identical books. This is a little bit complicated by, it's hard to actually figure out whether two books are exactly identical. May have different ISBNs, but one's a hardback, one's a softback, one's an audiobook. We don't want to still recommend that book. So there's clustering and text feature analysis that we try to do to understand that still topic-wise, these books are all too similar to what you've already bought. Let's try to find other stuff. And then it becomes this taste question of, well, of those other books, that are maybe in the same genre that you've been recently looking in of, say, historic nonfiction. What are the books that taste-wise match you best? So we sort of think of it as generating a recall set first, which are, here are 1,000 books that represent all of the kind of objective criteria that we think you're going to want. It's a book in historical nonfiction. It's not a book that we think you've already bought. Now let's use taste as a ranking of those 1,000 books to figure out which 1,000 we think is going to most closely match what you're going to like.
So you end up reading the coordinates.
Maybe 1,000 books. And that's one thing that just over time we want to read more and more and more. And there's a lot of work we're trying to figure out of how do you, this can leverage a lot of sort of geospatial indexing, because a lot of this querying becomes, find all of the items in a sphere that are closest to me, right? So there are better things to do in terms of how to query efficiently that recall set that we're still not doing, that we want to do.
Why you choose Cassandra? Do you want to any technical challenge when you build it?
So we've looked at a couple of different databases. So we have right now a large Mongo cluster running. This is one of several different large Cassandra clusters at eBay. And then we have some MySQL clusters. We're getting rid of the Mongo clusters. Basically, every week, Vulcan here buys more machines for Cassandra and trades in machines for Mongo. We're also buying more MySQL machines, in fairness, too, though. But to get to your original question about why we chose this is that theoretically, we think that this is the right architectural solution for a very high write scalability problem that inherently has a very data parallel architecture. Our recommendations, even though there's this graph that does connect everyone to everything, it can still be kind of divided into nice parallel updates that when you do write updates, you update your immediate neighborhood. When I do updates to myself, I update my immediate neighborhood. Those can go on concurrently in different parts of Cassandra. So architecturally, that high degree of write concurrency matched our problem, and we thought that Cassandra was just architecturally the right solution to it.
You have to rely on other tools to supplement this solution. Do you use Hadoop or your analytic application?
Honestly, we use all of the above. Whatever you're about to name, we use. So we have approximately 8,000 machines running Hadoop. We generate 10 terabytes minimum per day of logging data from the site. We have giant H-based installs also for building search indexes. So yes.
Are there any enhancements that you've made or that you're looking to make to Cassandra Core specific to solving graph problems, enhanced indexes, anything along those lines?
I'm ashamed to say we have not. We would like to. We haven't had the opportunity to. We actually were looking for an intern over the summer that might want to work on a few of these problems. So if anyone knows a great intern that would want to work on Hack on Cassandra to make it sort of adept to work on a couple of these kind of graph-related problems, we definitely are interested, but unfortunately we have not done that to date. Any other? Oh.
Are you using Cassandra only for the actually user preference, or just you're using in other sections of eBay?
We are using in other sections of eBay. So we're using it here to store this graph of people and things. There is, and I'm ashamed to admit, I actually don't know in detail some of the other applications. I know one of the other ones is around some social signals. So when people do Facebook Connect or tweet things, logging those connections. Those, I think, applications are a little bit more logging oriented, where the data is written and then queried less and overwritten less. I think maybe one of the interesting things about our application is that it's a very update heavy and read write of that data heavy workload. That is MySQL. So we tried MySQL cluster, had very bad results in terms of just bugs and not being reliable. We now just do our own sharding on top of MySQL, regular MySQL, InnoDB. So about 24 machines that just serve those recommendation coordinates out. So today, this cluster runs in one data center. So it's not something we've had to.
And how do you come up with a rep factor if you would think it makes sense?
I don't know. I don't know, Vulcan.
We started off at 2, and we're still in the process of like acquiring more machines, and it just takes a while. We want to ramp it up to 3, and we want to go to a second data center.
So for a graph-based, and you're using Cassandra, what is the most difficult challenge that you faced that Cassandra doesn't support, and you have to build your own algorithm or?
I don't know, Vulcan. Maybe that's.
This is you're trying to do a graph-based data structure on using Cassandra. Is there any of the feature that you looked at from the graph-based perspective that Cassandra did not provide you, for which you have to write your custom?
It kind of basically just worked.
Yeah, it did work more or less out of the box. If you're asking about like traversing the graph and those type of like features that other graph databases have, we never had to do those ourselves, and it mostly just worked. We're reading edges, reading nodes, pretty, you know.
Well, I mean, I think one thing that we've thought about is if we could push computation into the Cassandra cluster itself.
Yeah.
So instead of, right now our pattern is basically we read a ton of data from Cassandra into app servers. We do a bunch of, we generate a series of linear equations, we solve them, and we write the results back. Well, instead of bringing a huge amount of data to the app server, why don't we just push the computation into the database machines? And so like I don't know if we can do that with triggers someday. That sounded kind of intriguing, or maybe it's a bad idea and you'll tell us it's a terrible idea that we shouldn't do. But either way, that's the one thing we sort of thought about is because we do have a risk of saturating our networks. That's why we're going on like 10 gig Ethernet and things like that. With the amount of data we're pulling out of Cassandra to compute on and then push back in, it would save a lot of bandwidth for us if we could just push computation into Cassandra. I think we're almost out of time here. Maybe we are out of time. Oh, okay. Yeah.
Along the lines of pushing computation into the Cassandra cluster, have you considered embedding Cassandra itself into your application server?
We talked about that a while back, that we could actually just run our own app on the nodes or embed into our own app. And then for lack of time, we just didn't pursue that further. And there is a simplicity angle. But anything else? Great. Well, thank you very much.